So thank you for sticking with me in this long unit as we discuss this really important topic of MOS electrostatics. We're almost there. We've come to maybe the most complex part of the discussion. Small MOSFETs have 2- and 3-dimensional electrostatic effects. This requires a much more complicated analysis in general solutions, numerical solutions of 2- and 3-dimensional Poisson equations. Because of that, we're going to focus on trying to understand qualitatively what are the important consequences of 2-dimensional and 3-dimensional effects on MOSFET IV characteristics. So here's a sketch of a MOSFET. This is a bulk MOSFET of a few years ago, but the considerations are still very similar. There's an electrostatic potential that varies in X and Y, and in general in Z, the third dimension coming out of the page here. And how do those electric fields affect the device? Well, we'll just describe. This is what happens, and then we'll try to explain why. We're familiar with our transfer characteristics and with our dibble and plotting log ID versus VGS. And we know that there is dibble. We know that if we pick an arbitrary current and we say above that current the transistor is on and below that current the transistor is off, then we can define a threshold voltage. We get a threshold voltage when we have a low voltage on the drain. It would be called VT lin. And when we put a high voltage on the drain, there's a lower threshold voltage. We'll call that VT sat. And this is a consequence of the dibble that we've discussed a little bit before. So there's a change in threshold voltage with drain voltage, which is an undesirable characteristic. So the threshold voltage decreases as the drain voltage increases. We also find that at a fixed drain voltage, if you lower the gate length, shrink it, the threshold voltage can also decrease. That's an undesirable characteristic, to have different size transistors have different threshold voltages. And the dibble, this spread between these two curves also increases as the channel length decreases. These are undesirable effects that are due to 2-dimensional electrostatics. Well, there are some other things that can happen if the effects get stronger. We might find that the subthreshold swing changes, that the on to off, the off to on transition becomes less steep. That's undesirable. And that can happen as we increase the drain voltage. It can also happen as we decrease the channel length at a fixed drain voltage. So that's a more severe effect of 2-dimensional electrostatics. An even more severe effect can happen if the device punches through. In a case like this, you can see that there is current flowing, above threshold current flowing, even before we apply a gate voltage. So the transistor is not very useful at that point. We say that it's punched through. Another effect of 2-dimensional electrostatics is the finite output resistance. In an ideal MOSFET, or if we had a very long channel MOSFET, we would find that the drain current saturates and the output resistance, which is 1 over that slope, would be infinite. In real structures, we find that there's some finite slope. As we decrease the channel length, that slope gets steeper and steeper. The output resistance gets smaller and smaller. Okay, all of these effects come about from solutions to the 2-dimensional Poisson equation. If we want to solve the problem properly, we would sit down and solve these 2-dimensional equations. Things would get a little bit complicated, but that's what we would need to do in order to quantitatively understand these. And there are numerical simulation programs available that do this readily, and device design engineers spend a lot of time doing this so that they can design devices to minimize these effects. In this lecture, though, our goal is to develop a qualitative understanding of what's going on. So let's look at this VT roll-off, the fact that the threshold voltage gets smaller as the channel length gets smaller, or as the drain voltage gets higher. So that's a consequence of 2-dimensional electrostatics. When we discuss things like the mobile charge being Cox, Vg minus Vt, we were doing a one-dimensional solution of the Poisson equation into the depth of the semiconductor. If we plot the energy band diagram along the other direction, along the channel, then we can understand the two-dimensional effects. And we've discussed this a little bit before from the energy band perspective. The height of this barrier determines the current. If we apply a high VDS, we don't want to pull that barrier down, because in an ideal structure, that barrier height is going to be controlled by the gate and not by the drain. And the current then hops over that barrier, flows into the channel and out the drain. In any real structure, won't behave quite that ideally. When we apply a high VDS, we're going to lower that barrier at least a little bit. And if we have a well-designed transistor, it will be only a little bit. Because we've lowered that barrier a little bit, we're going to get exponentially more current. So that lowering of the barrier will reduce the current. That lowering of the barrier will reduce the threshold voltage, because now we have to apply a smaller gate voltage in order to push down the barrier and get significant amounts of current flowing. So that's how we think about that two-dimensional effect on an energy band diagram. If we increase the gate voltage, the drain voltage, we'll have more barrier lowering. Or if we reduce the channel length and bring the drain closer to the source, we'll also get more barrier lowering. Precisely how much, we would do a numerical solution of the two-dimensional Poisson equation. So if we have a small amount of barrier lowering, the threshold voltage is affected, the dibble increases, but the subthreshold swing does not change. We just have a parallel translation of those curves. As we have more and more two-dimensional effects of this nature, we can have more barrier lowering, and the subthreshold swing can also increase. And if we have a large amount of barrier lowering, things are catastrophic and we have punch-through. So here's an example from some real transistors. In this particular technology, we have a well-behaved transistor with a gate length, a channel length of 105 nanometers. So you can see we have a good subthreshold swing. The two curves are parallel. There is some dibble. That's a two-dimensional effect, but it's under control, and this is a useful transistor. If we look at the 85 nanometer, the shorter channel length in this technology, and if we define, a particular current, and we say above that the transistor is on, and below that the transistor is off, then if you compare the threshold voltage for the 105 nanometer device with the threshold voltage for the shorter channel device, you'll see that the threshold voltage is lower. The VT has lowered. This is a two-dimensional effect that became stronger because we shrunk the channel length. The dibble is also increased. You can see the spread between the two curves is increased, and you can see that the subthreshold swing is also degraded significantly. In fact, there is an above threshold current flowing in this particular transistor with 0 volts applied to the gate. So this device is punched through. It is not a useful transistor in this technology. So a punch through looks something like this. On a transfer characteristic, on an output characteristic, you would notice it would look something like this. So these are very poor transistor characteristics that essentially render the transistor of no use for us in good circuits. How do we think about punch through from an energy band perspective? So we think about it as what we've done is we've pulled the barrier at the source down so far that current flows immediately with no help from the gate at all. Electrons just spill out of the source into the channel and go out of the drain. That's an undesirable characteristic. No barrier to current flow at all. So the question is, how can we make sure our transistors are not punched through? How can we make sure that they have low amounts of dibble and that they have a good steep subthreshold swing? Well, we can do that. The concept of screening is important for this discussion. And I'll just remind you, if we think about a bulk semiconductor, not a small MOSFET, But a bulk semiconductor where we've doped it N-type, we have ionized donors, they'll be positively charged. They will attract the mobile electrons that are in the N-type semiconductor, and those negative charges will screen out or cancel the positive charge. If we solve this problem, what we find is that the potential is the bare Coulomb potential, the 1 over R potential, times e to the minus distance over some characteristic length. That is the screening length, the so-called Debye length. And that's the length over which the charge is screened out and the semiconductor becomes neutral again. And you can see this simple expression for the Debye length. It depends on the electron density. The more electrons there are, the shorter the distance it takes to screen out the fields and make the semiconductor neutral beyond that point. That's classic electrostatic screening. Now, in a MOSFET, there is a different type of screening. We could call this geometric screening. We have metal plates. We have a metal gate here on top, and we have a conductive substrate below. When we apply a voltage on the drain, there will be positive electric field lines that will emanate from the positive charges there and have to terminate somewhere. We'd like to see them terminate on the substrate, terminate on the metal gate, and we would like to make sure that they do not penetrate a great distance over to the source where they could begin pulling electrons out of the source and lowering the barrier and causing all kinds of problems. The distance over which those electric field lines from the drain penetrate, we would call that a geometric screening length, something like a Debye length, but now it's determined by the geometry of the transistor. If we can make that geometric screening length short, we can make sure that the drain voltage does not influence what goes on at the source, and we have a well-designed transistor. How do people do that? Well, that's been a main reason that in recent years, the semiconductor industry has moved from these planar transistors, where as we made the gate length shorter and shorter, it got harder and harder to control these barrier lowering effects, two-dimensional effects, moved to a FinFET, where there is a vertical fin of silicon that is the channel, and we wrap the gate around that channel as much as we can to try to control the potential in the channel with the gate voltage and screen out the electric field lines emanating from the drain. Now you can compute this geometric screening length. It takes a solution to the two-dimensional Poisson equation. I can refer you to a couple of papers if you'd like to see how that is done. But one of the takeaways is that the more fully surrounded the channel is by the gate, the shorter its screening length is. And the shorter its screening length is, this geometric screening length, the less influence the drain has on the barrier at the source, and the better the transistor operates. So a nanowire transistor where the gate is wrapped completely around the channel has the shortest screening length. A double gate structure where we have a gate on the top and a gate on the bottom, or in a FinFET, a gate on both sides, has a good screening length. And the bulk structure has the poorest screening length. So the move in recent years to FinFETs and extremely thin SOI structures and eventually to nanowire structures is driven by the need to control these two-dimensional electrostatics as the channels get shorter and shorter and shorter. So we've talked about some ways of understanding these two-dimensional effects. Barrier lowering just by drawing energy band diagrams, this concept of geometric screening length, which gives us a qualitative way to think about what we would observe in the numerical solutions to the 2- and 3-dimensional Poisson equation. There is a capacitor model that you can have a look at if you're interested, another way of looking at these two-dimensional effects. So let's get back. You know, what's important in our virtual source model is what happens at the virtual source, the top of the energy barrier. At that virtual source, the slope of the energy band along the channel is 0. That means that the derivative of the electrostatic potential in the semiconductor is 0. Now, if we've done things right, remember that dimension y is into the depth of the semiconductor. And that's the one-dimensional Poisson equation that we solve in order to conclude that the mobile charge is Cox, Vg minus Vt, and things like that. The distance y is along the channel. If we've engineered the device well, appropriately, then the curvature in the direction along the channel is much less than the curvature in the direction normal to the channel. That means we can use our MOS electrostatics to think about, at least at the top of the barrier, to think about what is the mobile charge as a function of gate voltage. And this is called the gradual channel approximation. It means we're going to go back and use that one-dimensional solution, and we're going to use it under two-dimensional conditions. But if we properly design the transistor, that's going to be adequate. So what that means is that at the top of the barrier, if we've designed our transistor carefully, we can say that the mobile charge is minus Cox, minus C inversion, Vg minus Vt. There will be some small influence of two-dimensional electrostatics through dibble. Dibble affects the threshold voltage. But we essentially have an expression that is very close to the expression we developed when we were only thinking about a one-dimensional Poisson equation, with the dimension being into the depth of the semiconductor. All right, so that greatly simplifies our analysis in these very short channel devices. And you ask, well, how can I know that that's going to be the case? Well, that is really the job of the device designer. Device designers spend a lot of time designing the transistors so that this does indeed occur. This is why we've moved to FinFET structures and will eventually move to nanowire structures. It's to produce what my colleague at MIT, Dimitri Antonidis, refers to as a well-tempered MOSFET. It's a MOSFET in which the charge at the virtual source, or at the top of the barrier, has this very simple relation that would apply in a long channel device or in a one-dimensional MOS capacitor. We have a small correction due to two-dimensional electrostatics through the dibble parameter delta. There is a region near the beginning of the channel where the slope is very shallow. The curvature of the band is very weak so that the one-dimensional electrostatics works. And that's the region that is strongly under the control of the gate with an M parameter that's close to 1. If we increase the drain voltage, we don't pull down the barrier in a well-designed transistor. The increased voltage is dropped near the drain end of the channel, and the source end of the channel and the virtual source itself are only very weakly affected. If that's the case, we have a well-tempered MOSFET. All right, so let's summarize. In this lecture, we took a qualitative look at two-dimensional electrostatics to understand how they affect important device parameters. Things like why the threshold voltage depends on channel length, why it depends on drain voltage, what causes dibble and subthreshold swing to increase, what causes punch-through and effects like that. The goal of MOSFET design is to minimize these two-dimensional effects as much as possible. And to make one-dimensional MOS electrostatics, this simple notion of mobile charge is Cox Vg minus Vt, to make that hold at the virtual source with only small corrections or dibble and subthreshold swing. To achieve that, we engineer the device such that the gate controls the height of the energy barrier between the source and the channel, and the drain has very little influence on that energy barrier height. Okay, so we've covered a lot of ground. We've talked about a lot of different things regarding MOS electrostatics. We're almost at the end of this unit. In the next lecture, what we will do is to go back and revisit our virtual source model, and based on our better understanding of MOS electrostatics and mobile charge, see if we can make that virtual source model a little bit better.